Alright, today we're going to be looking at projectile motion. The first thing we're going to do is get some definitions out there, and then we're going to be looking at the X and Y components of a horizontally fired projectile. So we're just looking at the horizontal projectile, not one at an angle. Okay, so we're just looking at if it was fired horizontally from a hill or a cliff or a building or whatever, and not at an angle. Okay, so here we go. Projectile motion is the motion of an object thrown or projected into the air subject only to the acceleration of gravity. Okay. So projectile motion is the motion of an object thrown or projected into the air, subject only to the acceleration of gravity. So the object is called the projectile, and its path is called the trajectory. So the object itself is called the projectile, and the path is called the trajectory. For all the problems that we're going to solve today, we are going to assume that air resistance is negligence. Or negligible, excuse me. So air resistance is negligible, meaning we're going to ignore it. We're going to pretend like it's not a thing. Okay, or at least if it is, it's so small that it doesn't affect our answers. And as a reminder from vectors, the X and the Y components are independent from each other. So we're going to be looking at this motion vertically and this motion horizontally. So we're going to draw a little picture, we're going to label some stuff, we're going to list out and define our variables, and then look at what equations we're going to use. Okay, so we're going to draw like a little cliff or building or hill that we've got, and we've got some kind of projectile, maybe a ball or a rock or a golf ball, soccer ball. The distance here of the cliff or building or hill we're going to call dy, and it's essentially the height of the building or hill. D for distance displacement, Y for the Y direction, meaning vertical distance. Okay, and then the path of this, it's going to be fired horizontally, so it will end up taking some kind of path like that. So this is the path we have it taking. It has a horizontal velocity, which we're going to label Vx. It's our velocity in the x direction. it will hit the ground at a specific time t. The distance that it travels in the x direction is called the range, and dx. So we're going to label that dx, which is our distance or displacement in the x direction. So this is how far will that projectile land away from the edge of that cliff or hill or whatever it was fired from. And then lastly, what pulls it down to the earth? Gravity. So we've got gravity here also. So we're going to list out our variables and define them in the x direction and in the y direction. So in the y direction, okay, we have dy, which is the distance it falls. We have g for gravity, which is always what number? 9.8 meters per second squared. And then we have t, the time that it takes to fall. Okay, dy, g, and t. Well, in the x direction, we have the velocity in the x direction. Velocity in the x direction. We have our dx, which is our distance in the x direction, or a range. And then again, t, the time that it takes to get there. Now about these two, we have time in both. Is that the same time? Is it the same object? So because it's the same object, that t is the same number. It's the same amount of time because that object is traveling in both the x and y direction. So I'm just going to make a note that t in the y direction is t in the x direction because it's the same time. Okay, the t is all the same. It's the same number. The equations we're going to use are familiar. We've used them before, but now we're going to make sure we specify x or y direction. So our distance in the y direction is 1/2 gravity times squared. And our velocity in the x direction is going to be my distance in the x direction divided by my time. These are not new. They're one we've used before, but now we're just really specifying the x and the y direction with this notation. And here, it's just fired horizontally. It's not fired down at an angle with a velocity. It's just fired horizontally. Okay, so I'm going to give you an example, and we're going to glue it on this page, and then we're going to solve it together, okay? All right, so let's take a look at this example. A rock is fired directly horizontal off a cliff that is 15 meters tall with a velocity of 35 meters per second, very fast. How long is the rock in the air, and what is the range of the rock? Okay, so first decide what you're given. So what are we given in this question? 15 meters, and then we have to decide what that is. So looking at our variables, it says that it's 15 meters tall. So the tall gives me the clue that this is dy. This is the distance in the y direction because it's telling me how tall or what the distance is going to be that rock falls. Okay, I'm also given 35 meters per second. I know that this is going to be Vx because it says velocity and the units are meters per second, okay? So I'm given dy and I'm given Vx. So I'm trying to find, it says how long is it going to take, so that's going to be t. And then the range of the rock, well, we know that range means we're talking about dx, okay? So what we just did right there and trying to figure out what it is we're starting with and we're given is really key to making sure that you plug them in the right places. So what we're going to do and what you're going to do for your practice problems is draw it out, list your variables, and solve. Okay, so here we go. We're going to draw it out for ourselves. So it really makes this a visual process. I've got a rock that I'm going to fire that is fired horizontally and has a trajectory. My dy, or the length of my cliff, or the height of my cliff, is 15 meters. I have a velocity in the x direction is 35 meters per second. The time that it's going to take to hit the ground, I don't know. The range, I don't know. But I do know that it's going to be affected by gravity at 9.8 meters per second squared. Okay, so now that we've got that drawn, we're going to list out our variables. And the reason for this is so that way when I go to solve, it's all neat and in one place, already separated into the x and y components. I can see what I'm missing and I can easily move on to the next part because it's all listed for me. So dy, and I'm just going off of the same variables that I listed here. I'm going to list down here and label with the numbers. So dy is 15 meters. Gravity is always 9.8 meters per second squared. My time, I don't know. In the x direction, vx is 35 meters per second. Dx, my range, I don't know. And my time, I don't know. So this kind of gives you some clues in the order in which you're going to have to solve this. So that way you can find all of the missing pieces. For example, I can't solve for dx right now because I don't have the time. I would need 2 of the 3 things in order to solve for that third. So it kind of gives you a clue of the order that you're going to have to do in order to solve this. Okay, so for A, it says how long is the rock in the air? Well, that means I'm solving for t. I can't use the x direction to solve for t because I'm missing dx. So I'm going to have to use the y direction to solve for t because I have 2 of the 3 things. So for this one, d equals 1/2 gt squared. I'm going to be looking for t, okay? A part where I've noticed students get mixed up is rearranging this equation and solving for t. So we're going to rearrange it on this post-it note right next to it so we remember how to do this and know how to do it. So distance equals 1/2 gt squared. All I'm going to do is move things around, okay, in order to solve for just t, so that way I can just plug it in. So the first thing I'm going to do is get rid of this 1/2 by multiplying both sides by 2. The 1/2 and the 2 cancel, so 2 dy, excuse me. So 2 dy equals gt squared. The next thing I'm going to do to get t by itself is divide out g. So I'm just doing some algebraic rearranging. So 2 dy divided by g equals t squared. So if I am trying to undo the square, you are going to square root. So we're going to square root both sides. Okay? And that square root is of this entire thing. So the entire part of that equation gets square rooted. So then t equals the square root of 2 dy divided by g. And this is what we're going to use to plug our stuff in. So all we did was rearrange this equation to solve for t. Okay? So if I rewrite this, so it's the equation I need, the square root of 2 dy divided by g equals t. So now that I've rearranged it, I'm going to plug it in. Okay, so here we go. Square root of 2 times dy, which is 15 meters, divided by g, which is 9.8 meters per second squared. The meters and the meters will cancel. And then 1 over second squared. The second squared gets flipped to the top. So I'm going to solve this stepwise. So I'm just going to do what's inside of the square root first. So 2 times 15 divided by 9.8, 3.06122. So this is going to be the square root of 3.0612224. And I'm not going to round yet because I want the most accurate answer at the end. Okay, second squared. And so now I'm going to square root this. So you can hit second square root second answer, or I can multiply this or put it to the exponent of 1/2, and that's the same as square rooting. So what I would end up with here is 1.75 seconds. So you could also do second square root 3.061224, and there we go, 1.75 seconds. So this is t. So this means that it took 1.75 seconds for this rock to fall off this cliff. Now we've got t. Okay, so now part B says, what is the range of the rock? So now that I have the time, I can rearrange the equation and solve for dx. So that's part B. So part B is, I know I'm going to be using my x component now. So my x component variables, and Vx equals dx over t. So to rearrange this equation to solve for dx, if I multiply both sides by t, then I can get dx by itself. So Vx times t equals dx. All I did was rearrange it by multiplying both sides by t. Okay. Now I can just plug it in and solve because I have Vx that was given to me in the problem. I solved for t in the previous question. So Vx, 35 meters per second, times t, 1.75 seconds. Seconds and seconds cancel. So then we're just multiplying 35 times 1.75 equals 61.25. So 61.25, and the units are meters because it's the only thing that didn't cancel. Okay, so let's talk about what all these numbers mean. What did we just find? A rock that was fired off a cliff that's 15 meters high at 35 meters per second took 1.75 seconds to fall and landed 61.25 meters away from the edge of the cliff. That's what it means. So this is how we're going to solve our horizontally fired projectile motion questions.